Okay, hello everybody. Let's start today's lecture. I'm sorry I missed last week's lecture, but you were supposed to watch a video that I made last year. It was about part of speech tagging. So that video was important. I hope you watched it. I checked the video analytics from YouTube, and I saw that like maybe 20-30 people watched it. So don't ignore that video. I am not going to go back and redo the lecture about the part of speech tagging. Especially end of the lecture, there is this talk about using the dynamic programming or Viterbi algorithm to do the assignments of the part of speech tags. That was important, and we are going to use, and the idea was actually the same as the edit distance. So we are gonna use the same dynamic programming idea in our parsing chapter to chapter number 13. So that was important. I hope you watched it. If you didn't, you go back and watch that video. Okay, today I will start a new topic. It is formal grammars. Today I am hoping to finish up with the basics of the formal grammars. Next week we will talk about the real grammars of English and Turkish. So come on. Today we will talk about grammars, context-free grammars, CFG, and then we will make an introduction to English grammar, and we will talk about our data sets about the tree banks. It's like the part of speech banks or the n-gram banks. There are tree banks for English and Turkish, and there are some cases where this context-free grammar approach or the regular grammar approach for English or for Turkish doesn't work. In that case, we are going to look at this dependency grammars topic. That's what we're going to do. Well, obviously, the topic of this grammar is syntax. By syntax, we mean the rules about how the words come together, how we order the words, and in relation to each word, how they affect their appearances in a sentence. And this will be a little bit different from what you know as the grammar of a language in Turkish or English. It will be a little bit different because we are going to use formal mechanisms to explain the syntax. So some parts will be similar to what you already know. Some parts will not be that similar. So you don't have to know much about the grammar or the linguistics to understand what kind of grammar we are using with our approach. Okay, so it is your basic knowledge about the language, English or Turkish, should be sufficient. Okay, so the syntax, that means how the words come together, the order of the words and their effects on each other is important. We should care about it. It's a very hot natural language processing and natural language generation topic. We should care about it. Grammars are key components in many applications. Parsing and grammars, okay, grammars and parsing, they go hand in hand. They are always mentioned together. Parsing is this: given a sentence, determining if that sentence belongs to a language grammar. Okay, can I explain that sentence in terms of that language grammar? Is the process of parsing. When you do the parsing, the answer is not just yes or no. I mean, when you do the parsing, if the grammar doesn't fit to the sentence, you would say, yeah, no, I cannot parse this sentence. Also, when you say yes, you would find a parse tree. You say that, okay, this sentence parses, and this is the parsing tree. That's the process of parsing. But we will not talk about automatic ways of parsing a lot in this chapter. That will be the talk of next week. So if we are successful at parsing or producing grammars for a language, where are we going to use them? These are some of the sample applications. One of them is, for example, grammar checkers. You know, your favorite word editing software such as Microsoft Word sometimes gives you pointers about the grammars of the sentences, such as it says that there is a disagreement between subject and object of this sentence. You cannot say children runs, you have to say children run. Okay, sometimes the word application gives you this kind of feedback. Dialogue management, again, if I am in a dialogue with a computer, if I am asking a question, how many people are there in Gebze Technical University? That's the question. Without parsing my sentence, the computer cannot know what is being asked. The question is answering is very similar. What is the question? What are we answering? Information extraction, again, you have a very large text, such as the text on the web, and I am asking questions. I am trying to get information such as the size of the Turkish population over the whole world. Again, machine translation comes up very frequently when we talk about natural language processing. Without parsing a sentence in one form or another, you cannot make machine translation in a healthy, in a sound way. So these are some of the applications of parsing or applications of grammar. So let's look at the grammars more carefully. This chapter will be mostly about constituency. This is important, constituency. Constituency is grouping of words, okay? Grouping of words, and we are going to talk about it a lot. And then, other than constituency, sometimes constituency is very powerful. Yeah, it is very powerful, but sometimes it is overkill. Sometimes it is too much, and some of the languages are not very good about this constituency grouping of the words. For those kind of languages, we talk about grammatical relations. What are the relations between two words of a sentence? Okay, and we call them dependencies, and we are going to look at them. So the most of the talk about this, on this chapter will be about constituency and the relations between words in a sentence. Okay, and we are gonna see which one is better for what languages and under what kind of circumstances we use which one in this lecture. Okay, so to do this constituency analysis, we are gonna use context-free grammars. And I think you have seen context-free grammars in programming languages course because our regular programming languages, such as C or Java, they are all explained, they are all expressed using context-free grammars, CFG for C language, context-free grammar for C language. Okay, let me see, can I find it? Yeah, it's coming back. Yeah, okay. So these are some of the rules for the C language. Okay. So a program is a declaration list. A declaration list is a declaration list, recursive, and declaration, etc. We are going to come back to this together. So this is a grammar for the C language. Okay, the grammar for the C language. We are going to do similar stuff for the English and Turkish. Okay, and we are going to see the differences between the grammars for natural languages and the grammars for the formal languages such as C and Java. Okay, there are many. How many rules are there? There are 43 rules, and it is, as you know, C is a design language designed by the humans. So the number of rules are fixed. You cannot add more rules. You cannot remove any of the rules. But for the natural languages, the number of rules is not fixed because we did not design Turkish or English. Okay, they are natural phenomena. That's why we do need to do the reverse engineering and try to fit the try to extract the context-free grammar for a given language. And if you do that, sometimes you may end up with thousands of rules. Like for English, in one of the data sets, we have 4,500 rules. Okay, so we are gonna see them one by one. Okay, so context-free grammars is going to, we are gonna use them to express our grammars for English or Turkish or any other natural language given to us. As always, we will have our data sets, and in our cases, they're going to be tree banks. Why do we call them tree banks? Because these data sets include sentences, and for each sentence there is a parse tree. That's why we call them tree banks, and we are gonna look at one or two of them carefully. Okay, good. So let's go back to constituency. Constituency is one of the main ideas of context-free grammars. Okay, so constituency means that it's the grouping of the words. Grouping of the words. Okay, grouping of the words within utterances. We say that a word is a meaningful structure in a language, but if you group a number of words together, they show some other meanings. They show some, they make sense in some other way. These units, okay, they form coherent classes in terms of their relationship with the other units. Okay, they behave in a similar way in terms of their structure with respect to other units, and also they show structure with respect to their internal structure. Okay, so two things, they have some internal structure, these constituencies, and they have some relationships, specific relationships with the other constituencies in the same sentence. So to make more sense about what I am telling you right now, maybe I can give you an example. For example, this word horse is a single word in English, but when you say Harry the horse, or the Broadway coppers, or they, okay, this one, or a high-class spot such as Mindy's, or three parties from Brooklyn, okay, We call them noun phrases in English. İsim tamlamaları, noun phrases. Okay? These are constituencies. They come together and we call them noun phrases. And these noun phrases, as we said before, they have their own internal structure. There are rules for noun phrases to come together. Okay? For example, the three parties from Brooklyn has a internal structure. There is a noun phrase and a propositional phrase after that. Okay, we can say that. That's one thing. So each of these noun phrases have their own internal structure. That's one thing. Also, there is another evidence that says that these are constituencies, because after each one of these noun phrases, I can put a verb. Okay, for example, Harry the horse races. Okay, the Broadway coppers are very fine. They came. Okay, a high class spot such as Mindy's is expensive. Okay, so I can put a verb after each of these noun phrases. So it is like there is the noun part of the sentence and there is the verb part of the sentence. And these constituencies, these grouping of words, are behaving in a way that they have their own internal structure. Also, they have certain relationships with the other structures in the same sentence. Okay, so usually we are gonna say is that if you have a sentence in English, and I'm going to show it with an S, that sentence usually is expressed like a noun phrase and a verb phrase. Okay, when I say Harry the horse is a noun phrase. Okay, Harry the horse races tomorrow. Okay, this part is a constituency, it is noun phrase. This part is a constituency, it's a verb phrase. Noun phrases and verb phrases, they have their own internal structure and they have relationships with each other, because in English, noun phrases come before the verb phrases. Okay, and they have to be compatible with each other. That's what we are saying in this case. Okay, these constituencies are groupings of words, but they are not ordinary groupings of words. They have their structure, internal structure, and they have their relationships with the others, like internal structure and external behavior. Okay, so the constituency is the general idea of using groups of words in a sentence. It is similar in a programming language. Okay, for example, the constituencies in a C program could be maybe functions, right? So a C program could be a collection of function definitions, and each function is a constituency. But within the function, there are other constituencies, such as the declarations, such as the executable statements, and etc. Okay, so that's the whole idea of constituency, and our task is going to be finding these kind of constituencies for the English language or Turkish language, and these rules, each one will make a context-free grammar rule for our grammar. Okay. As I said before, natural languages are, as the name implies, they are natural. They are not designed by humans. Okay. So when we say that we are going to come up with the grammar for Turkish or English, that doesn't mean that it's going to be easy. And that doesn't mean that the grammar that we are going to find for Turkish or English is going to be complete. Okay, it doesn't have to fit the whole language. Okay, that's why there are so many different theories about grammar. There are so many theories about how to express these kind of rules for any given natural language. We don't have the same problem for C or Java language because, as I said before, it is designed by humans. And if there is a problem with the C language grammar, we can easily fix it, and we say that there was an error and we fix it. I cannot say the same thing for Turkish or English. Okay, I cannot say that I am changing Turkish so that we are going to talk Turkish that way or this way. I don't get to do that. The approach in this chapter that we are going to take is very, very generic. Okay, and it is computationally motivated, and there might be more complicated approaches, but the grammar that we are going to produce for English or Turkish is going to be very, very generic, and that will give you the basic idea about the constituency and the context-free grammars. Okay, so let's check the context-free grammars in that case. Context-free grammars, as I said before, is a formalism that you already know from the programming languages courses. Also, sometimes they are called phrase structure grammars or Bacchus form. In a given context-free grammar, we have three components. We have rules, we have terminals, and we have non-terminals. Okay, rules, terminals, and non-terminals. And in fact, actually, before looking at this context-free grammars, let's check out the types of grammars of Chomsky hierarchy. Chomsky in 1950s, where is my Chomsky? Oh, okay, I got this from Wikipedia. Maybe I should open this using draw board so that I can draw on it. Okay, Chomsky says that, okay, the grammars for any language can be categorized into either type 0 grammars, type 1 grammars, type 2 and type 3 grammars. Okay, and each one is going to have a different name. Type 0 grammars are the most general grammars. They can explain anything. Then type 1 grammars, we have the context-sensitive grammars. Then context-free grammars and our regular expressions. Okay, regular expression is the smallest one. What are regular expressions? We already know them. Where we know them? Because finite state automata can do the regular expressions. For example, I remember our the sheep language. Remember our sheep language. This is a sheep language word. Also, this is a sheep language word. Remember, I think we did something like this: BA plus and that, right? What does this mean? For a sheep language to be correct, I need a B, I need at least one A, and as many A's you like, and at the end there has to be an exclamation mark. Okay, that was a regular language, and we use that a lot. Those regular languages, we use that a lot. Then after that, there is context-free, then context-sensitive, and the recursively enumerable languages. Okay, recursively enumerable languages. And let's see their differences. Okay, maybe I should keep this open, and I should go back and forth between this and my other slides. But let me tell you this: regular expressions Okay, regular languages are the most restricted one. And with the finite state automata, okay, I can produce regular languages or recognize them. Okay, finite state automata, you already know that. You remember what finite state automata is. There has to be states, there has to be transition rules, remember. There should be a start state, and there should be final states. That's what we know. Context-free grammar, we are going to look at them today. To understand, to parse a context-free grammar, we need a non-deterministic push-down automata. It's an automata, finite state automata, but it has a memory. Okay, it has a stack with it. And then we have the context-sensitive languages and recursively enumerable languages. So we are gonna look at them one by one. Let me go back. What's going on? Okay. Let me go back to my slides and okay. So in a context-free grammar, I have three components: rules and terminals and non-terminals. Terminals are for a language, Turkish or English, are words. Okay. I mean, if you consider punctuations as like words, we could say that terminals are words, including the punctuations. Non-terminals are the ones that represents the constituencies. Okay, like a noun phrase or verb phrase or sentence. These are all constituencies. Okay, and then we have rules. Rules are the equations that tells us how the constituencies and terminals come together. Okay, they are the equations that tell us how the non-terminals and terminals come together, their numbers, their order, okay, and their types. If I go back to the C grammar here, okay, these 43 things, each one is a rule. Okay, each one is a rule, and the things that are written in italics are constituencies or the non-terminals. Okay, here says that let me okay, in our case, in this case, this integer, boolean, and characters are our terminals, our words in C. Type specified is a non-terminal or constituency. A constituency could be either integer, boolean, or character, it says. Okay. A params, for example, a function declaration. Function declaration says that there should be a type specifier return type. Okay. Then there should be a function ID, and then there should be parameters, but before the parameters there should be a parenthesis and parentheses, another parenthesis, then the statement. Okay, and the parameters are like either empty or a parameter list. So the parameter list is expressed as recursively parameter list, okay, and param type list. So as you see, it is recursive. And it is, when I say it is recursive, I can use the same rule over and over again. Again, let's not talk too much about the C programming language or any formal language. Let's talk about English. Let me go back to this slide again. The rules are like that, and we are going to write similar kind of rules for English. Okay, for English, our terminals are going to be our words. Okay, for constituencies we have non-terminals, and we are going to come up with some examples. For example, for the non-terminal noun phrase, I have these three rules. Okay, let's try to explain them one by one, what we mean by them. Okay, let's try to explain them. Noun phrase There is something funny happening with my monitor. I'm trying to save it. Okay, so noun phrase is composed of a determiner and a nominal. Okay, these two are again non-terminals, constituencies, or noun phrase could be a proper noun. Okay, so these are the two rules for a noun phrase. And then I have a definition for nominal. Nominal is a generic name, more general name for a noun. Nominal could be noun or nominal could be nominal noun. So it's a recursive definition. Okay, it's a recursive definition. And in a few minutes, too bad I lost my, what's going on? Come on. My monitor switched off. Okay, looks fine. Okay, so in a few minutes I am going to show you a few examples about this this noun phrase and nominal rules, or maybe I can nominal, okay, noun, okay, good, okay. Nominal, noun, and okay, I'm trying to figure out a very simple example so that it doesn't confuse us. Okay, just the man. Okay, this is a noun phrase, right? The man is a noun phrase. So how do I parse this? This is what I do. Noun phrase, I started with a noun phrase. I started with determiner and nominal. Determiner is the, nominal in this case is going to be noun, and noun is going to be man. Okay, so the and man are terminals. Okay, determiner is a non-terminal. So these are our words that we see in a sentence. So I have parsed this piece of this sub-sentence using these just four simple rules. Okay, this could be considered as a maybe a single rule or two rules, because it is either this one or that one. Nominal. Okay, so and this is important, this nominal thing, recursive. I could do this recursively many times, and we are going to see examples of it in a few minutes. So some noun phrase rules, and I am going to make this more expanded. As I said, if you like to do the similar stuff for the whole English language, it's going to take thousands of rules. In this case, it is just very simple. Okay, so let's look at this simple L0 level grammar. This one says that a sentence is, in an English sentence, is noun phrase and verb phrase. Of course, this is a declarative sentence. It is not about, I mean, the question sentence cannot be like that, okay? In a question sentence cannot start with a noun. It has to start with a verb like, is there such and such, do you such and such, right? So this is a part of the language, not the whole language, but part of the language. It says that a sentence is noun phrase and verb phrase. There should be two constituencies in a sentence. The first one should be noun phrase, then a verb phrase. An example here is this. This is our noun phrase, okay, and this is our verb phrase. In this case, I was lucky my noun phrase included a single pronoun, but verb phrase includes 4 words. So how do I define the internal structure of a noun phrase? It says that noun phrase is either a pronoun such as I, you, she, he, etc. Or it could be a pronoun, özel isimler, such as Los Angeles or Istanbul or Ahmet or etc. Or a noun phrase could be a determiner and a nominal, such as that we did before, right? A determiner and nominal, a flight. And nominal could be nominal noun, okay? Or nominal could be noun, and like that. So this part is recursive part. When you do this nominal noun, okay, in this case it is morning flight, or it could be early morning flight, early morning expensive flight. Okay, I can put as many adjectives as I like before the last noun. That's why it is, okay? Early morning, expensive, comfortable, late flight, for example. You could put as many nominals as you like, because there is this recursive relationship in there, right? And this is the structure of the noun phrase, this part. And this is the structure of the verb phrase. Verb phrase could be very simple, just a verb. Or after the verb, there could be a noun phrase. See, noun phrases, verb phrases could include noun phrases. Okay? Want plus a flight. There are these type of verbs, right? That takes a noun phrase. Or there could be verbs that takes a noun phrase and prepositional phrase. Leave Boston. Boston is noun phrase and the prepositional phrase. Okay? Or just a verb plus the prepositional phrase. What is a prepositional phrase? It's like this. Prepositional phrase is a preposition such as to, from, in, right? Those are the prepositions, and the noun phrase. So it's a very simple L0 grammar. Very simple grammar, and it explains some part of the language, not the whole language, but just some part of the language. So who comes up with this kind of grammars? Who comes up with this kind of grammars? Computational linguists, they do that, and they do this with the help of maybe the classical linguists too. But I explain them in a context-free grammar way. What is our context-free grammar? Context-free grammar says that you are going to have the rules, you are going to have the terminals, and you are going to have the non-terminals. So how many rules do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11 rules, okay? And how many terminals and non-terminals do I have? These are all our non-terminals. Where are the terminals? Terminals are these words, okay? These are our words, okay? So how do I structure this context-free grammar? Let's go back to our discussion on Chomsky hierarchy. Chomsky says that if your rules are like this, okay, let me give you some explanations. Capital letters, okay, capital letters are non-terminals. Those A's are terminals, okay, And those alphas and betas and gammas are anything. It could be anything. So on the right hand side, if you have a terminal or terminal and a non-terminal, this could be a regular expression or a regular language. Okay, such as our sheep language. Remember the sheep language? How do I explain the sheep language with a regular expression? I would say a sentence could be, yeah, somebody try to write the sheep language using the regular language. A sentence is, remember the sheep language, it is BA plus, okay, but in type 3 languages we don't have pluses and that kind of stuff. So sentence is what? Somebody tell me what a sentence is in a B language. You guys are hearing me? I hope there are 34 people. Somebody write something. So as goes to what? Let me give you a hint. S should start with a B. Right? Then S should end with a exclamation mark. What should I write in between? But if you just write A, that makes this only a sentence. Or you mean that if I do that, maybe I can write B-A-A and then S-B-A-A-A like that. So I write this as many times as I like. Okay, Nida has an idea. Say that don't do that. Don't do that. Do this instead. Instead, do this. So B A exclamation mark, and A is either A or AA, like that, right? Okay. But the problem is it has to be either that way or this way. So my first rule kind of violates this, right? It says that it should start with a terminal and there should be a non-terminal, or it should be a terminal. So how am I going to prevent this? I cannot have a rule like this. I cannot have a rule that ends with a terminal. So how do I do that? SBA, then a exclamation mark, or AA. Yeah, yeah, that should work, right? So I get this one out, and or it is either a exclamation mark or AA. So if I have a BAAA exclamation mark, how do I do that? S BA, then after that AA, and after that A. Let me get rid of one of the A's here because that was too much. Okay, A and exclamation mark. Okay, so that's a regular language. Okay, type 3 grammar. Okay, the problem with these kind of, the advantage of these kind of grammars is with the finite state automata. You remember the finite state automata? I could handle these kind of languages very convenient, in a very convenient way. No problem. Okay, no problem. I can do that. But the problem with this kind of languages is I cannot handle this kind of balancing. Okay, an expression that starts with a parentheses should end with a parentheses, or just balance the parentheses. An expression that starts with a parentheses should balance these parentheses. Okay, I cannot do that kind of stuff. For that, I need this kind of a structure. On the left, there is a non-terminal. Okay, on the right, there could be anything. So this one, context-free grammar, says that I am restricting you to have a non-terminal on the left. On the right, you can do anything. It could be a mix of terminals and non-terminals on the right. Okay, that's called context-free. If I move one step up, context-sensitive languages say that on the left, okay, there should be at least one non-terminal. Okay, and around the non-terminal you can have terminals or non-terminals, doesn't matter. Okay, and on the right I should have the same alpha and beta, and in between there is you can put anything like that. Okay, so can you guys tell me, why do I call this a context sensitive and why do I call this a context free? Type 1 is context sensitive, type 2 is context free. Can anybody tell me why they have chosen these terminology, context free and context sensitive? Yeah, what you guys are saying is correct, yes. Type 2 says that whenever I see an A, a non-terminal, I can replace it with this gamma. This one says that whenever you see an A, don't hurry, okay? Look at where A happens. Look at the context of A, okay? Wherever it happens, it depends on the context. If your context is alpha and beta, then I am going to do this. If your context is different, if you are happening in a different place, then you might behave differently. Okay, so that's called, it is context sensitive. We like context-free languages as computer scientists better than context-sensitive ones because there is a very nice push-down automata algorithm. All of our compilers are like that, and we can parse. It is easy to parse sentences using this algorithm. It is very, very efficient, and we are going to see how it is done. When it comes to context-sensitive languages, okay, linear bounded non-deterministic Turing machine is required, and it is expensive to run that kind of a machine. Okay, so we up to now we did this regular expressions with our finite state automatas. Okay, now we are gonna do the context free. As I said before, our regular expressions, our regular languages are not powerful enough to handle the complexities of the natural languages. Okay, we need the context-free languages to be able to express the grammar of a natural language. Even the context-free languages are not going to be sufficient for some cases, but we will find some workarounds. But with the regular expressions, it is not easy to. With the regular expressions, I cannot explain anything like this. 3 plus 5 times 3 minus 2. Okay, this balancing of these parentheses is not possible. Okay, and the same stuff when you start a sentence with I, or let me give you an example. When you start a sentence with Turkish sentence with ben, something something something something, at the end there should be a verb, okay, that is compatible with ben. Okay, so this kind of balancing should happen with Turkish or English, and regular language is not powerful enough for that. Okay, I think I'm out of time for the first part of this lecture. Let's take 10 minutes of break. Let's be here around 14:35. 10 minutes of break. Okay, so context-free grammars are the grammars that we prefer. I have a question for you. When we say that our languages, formal languages such as C or Java, we express them using context-free grammars. So the meaning of this, A is assigned the value of B, should be fixed, right? I mean, the meaning of assignment should be the meaning of assignment. There should not be any ambiguity, but we know that it depends on the type of A and B if I can do this assignment. So it depends on the context. So how do they deal with this problem? Or when you say A plus B, the meaning of plus changes depending on the types of A and B, right? So it depends on the context. So how come I can use context-free grammars to express our C or Java language formally? Can anybody take a guess? Without tokenizing, you wouldn't know your terminals. I mean, without tokenizing, you cannot do even the regular languages. Yeah, I tokenize it. A is a token, B is a plus a token, and B is a token. Then they are all non-terminals, or they are terminals. So how do I know the meaning of plus in there? Because I need to know type of A and B. Without knowing types of A and B, I cannot know the meaning of or the parse tree for plus, because that plus could be string addition, concatenation, or double addition, or some other type, I don't know. We keep them ambiguous. We say that it's a plus operator and we don't know what kind of operator it is. We make a decision later. So even context-free languages are not powerful enough to handle all the issues with the formal language like C and C++. Okay, so we have to do some additional stuff. Okay, good. So are there any? Okay, type 2 grammars, LL parser, you know that, right? LL parsers, we use them for type 2 grammars and they are very, very efficient. Okay, good. Let me go back and do our discussion about natural languages. So this is one grammar for English. Of course, this grammar for Turkish doesn't work. And this is very, like, maybe a small part of the whole English grammar. Like we did with finite state automatas or finite state transducers, I could use these rules to parse a given sentence, or I could use these rules to generate strings in a language. Okay, either rejecting strings not in the language or generating strings in the language. Okay, so these are useful in both ways. The idea is similar to what we did with the finite state automata and finite state transducer. Here is a sample derivation of these of a sentence using these rules. I have a sentence, I prefer a morning flight. That's the sentence. I prefer a morning flight. Noun phrase and verb phrase. Here, noun phrase becomes a pronoun and pronoun is I. Verb phrase is divided into two, verb and noun phrase. Verb prefer is a verb. Noun phrase determiner nominal. Nominal noun. Nominal becomes noun and morning. And noun is flight. Okay, so it looks like I have used this nominal 2 times, the recursive definition. And as you see, I have covered all the elements in the string. 1, 2, 3, 4, 5 words in the string in my sentence, and all of them are covered. And I covered only the elements in the string. Okay, so that means that I have a successful parse tree of this sentence using these context-free rules. Okay, so it's a simple derivation. Sometimes I can have more than one derivation for the same sentence. In that case, I would say that there is ambiguity. There is ambiguity for that sentence, and it might happen. That's what we said at the beginning, right? At the beginning of the semester, that natural languages, especially sentences, they could be ambiguous. They might mean more than one thing. And for each meaning, we will have a different tree. So whatever parsing technique we are going to use, okay, whatever the parsing technique we are going to use is going to be producing many trees for the same sentence if there is ambiguity of the sentence. Okay, and we are going to see examples of it. Formally, I give a context-free grammar is composed of these 4 components. Okay, N is a set of non-terminal symbols. Okay, in this case, our N is S, NP, VP, pronoun, verb, NP, etc. These are our non-terminal symbols. Sigma It is different from an. Okay, it's our terminal symbols. In this case, those are our words and punctuation marks for natural languages. And R is a set of rules in the form of a terminal, a non-terminal on the left, and no restriction on the right. Okay, so A has to be a non-terminal, beta has to be a infinite set of strings from this set, union of sigma and n. And S is designated as a start symbol. Sentence or start symbol, it is the same for us. Okay, it's the same for us. So if for this grammar, S is the start symbol, and these are our non-terminals, and terminals are these. So formally we define a context-free grammar like that. And parsing is the process of taking a string and a grammar and returning either a single parse tree or many parse trees. Okay, single parse tree or many parse trees for that string. Okay, it is very similar to running a finite state transducer with a tape. Okay, remember with the non-deterministic finite state automata, it would be possible to have more than one accept state for a given string. And it is very similar in this case too. For a given sentence, we might have many different parses, and I think I have shown you this many times maybe. I saw a man with a telescope. I saw a man with a saw a man with a telescope. Okay. I don't want to see the slides. I should have maybe this one. Where is the okay, this is good. Yeah. Okay. See, the boy saw the man with the telescope. Okay, question. Do you see this one on the right? You see this one? Or maybe I should make this larger. Okay. Translate the first sentence to Turkish and translate the second sentence to Turkish. Somebody translate the first sentence to Turkish.
Çocuk adamı teleskopla gördü.
Çocuk adamı teleskopla gördü. And translate the second one.
Çocuk teleskoplu adam gördü.
Yeah. So çocuk teleskopla adamı gördü is second one. Çocuk adamı teleskopla gördü is first one, right? So these two sentences are written exactly the same, but their parses are different. whatever parsing method we are using, that method should produce these two trees, and they should say there is ambiguity in this sentence. That's okay. How do we deal with the ambiguity? One of the methods was find all the ambiguous analysis and expect that it will be resolved. It will be resolved in a subsequent phase, right? Or sometimes, if the two languages are similar, then if you are doing the machine translation, leave the ambiguity as it is. But in this case, if we translate from English to Turkish, I cannot leave the ambiguity as it is, because the same ambiguity cannot happen in Turkish. I cannot come up with a sentence that keeps the ambiguity. Can you? Teleskoplu adamı gördü, teleskoplu adamı gördü. So in English it is they are the same. One is in Turkish, no. Teleskoplu adamı gördü, teleskoplu adamı gördü. No, they are definitely different. They are definitely different. So go back to this one. Parsing is the process of taking a string and producing probably multiple parse trees. Okay. So for English, we have sentences, we have noun phrases, and we have verb phrases. Those are the main categories of the constituencies, okay, constituents, or the non-terminals in English. And let's look at the main sentence types in English. Declarative sentences, the sentence type that we have looked at a few minutes ago. A plain left, okay. Noun phrase, verb phrase. Declarative, you are saying something. There are imperatives, emir cümleleri. Just verb phrase. You don't have the noun phrase. Yes, no questions. Did the plane leave? It should start with an auxiliary, then noun phrase and verb phrase, right? And WH questions, who, where, when, why questions, right? So WH, MP, then auxiliary, then noun phrase, verb phrase. So these are 4 basic sentence types in English grammar, and each one is composed of these noun phrases and verb phrases. Okay, this auxiliary is simple. It is did, is, etc. Right? Does, do, have, etc. So it is this one is again when, why, etc. Is simple. So noun phrase and verb phrases is the complicated part. Let's look at them one by one. This noun phrases, okay. Looking at this rule, noun phrase determiner, okay, plus the nominal. Nominal, as I said before, is a generic version of a noun, okay, more general than a noun, and we are going to use it for our recursive noun phrase estimations, okay. And most of the complexity of English noun phrases is hidden in this rule. They modeled in that way, okay. If I consider this the derivation of this noun phrase, okay, this is not a sentence, this is a noun phrase. All the morning flights from Denver to Tampa, leaving before 10. This noun phrase is about flight. When you say all the morning flights from Denver to Tampa leaving before 10 is cancelled, okay, when you say this, that noun phrase is about flights. I could have said the same thing like the flight is cancelled. Flights are cancelled, right? So kind of the same meaning. So the noun phrase is dropped to just flights. Other than the flights, all the rest of the words are giving more information about the flight. Okay, so that's why this word here is important. Okay, and we are going to call this word head. head of the noun phrase. It is the head of the noun phrase. Okay, and this is the parse tree of that noun phrase. All the morning flights from Denver to Tampa leaving before 10. So what was the rule? Determinate and nominal. Nominal is the, okay, it looks like nominal gerundive VP verb phrase, ing verb phrase, nominal prepositional phrase, nominal prepositional phrase, nominal noun, and noun. So 1, 2, 3, 4 nominal rule applications. As we said before, okay, most of the complexity of English noun phrases is in. So 4 times the application of that nominal rule, or 2 times the application of the same nominal rule. Nominal proposition, nominal proposition. Okay? Good. So we will have similar stuff with the verb phrases. It will have some complications, but it will not be, I mean, this kind of nominal kind of application will not be there with the verb phrases. Verb phrases, as they have their own complications. Okay? As I said before, this noun phrase is about flights. Okay? That's the central critical noun. It is about flights, but I am giving lots of other information about the flights. I am talking about the morning flights. I am talking about the flights from Denver. I am talking about the flights to Tampa. And also I am talking about the flights leaving before 10. Okay? So flight is the central thing in here. That's why we call this the head of the noun phrase. Okay? So we can dissect this kind of a noun phrase into stuff that can come from the head and stuff that can come after the head of the noun phrase. Okay, so the determiners, okay, noun phrases can start with the determiners, can be the, des, a, and etc., a car. Okay, or determiner can be a possessive, car but John's car, or complex recursive determiners, John's sister's husband's son's car. Okay, car is the head here, and before that there is a recursive application of the determiners. Okay, so again, this is done by that nominal mechanism again. Nominals contains the head and any pre and post modifiers. With the nominals, with the pre modifiers, I have the quantifiers, cardinals, 3 cars, adjectives, large cars, or 3 large cars. See, we don't say large 3 cars, so you need to be careful in there while you are extracting the rules. And these kind of things are going to create problems. You don't say large 3 cars, okay? You say 3 large cars. You then say 3 yeşil araba. You say 3 yeşil araba, but you don't say yeşil 3 araba. Okay, so with this kind of modifiers, pre-modifiers, or post modifiers, you need to be careful about the types of the adjectives. Post modifiers, again, I have the post modifier, nominal prepositional phrase, okay, like flight from Seattle, nominal gerundive verb phrase, flights arriving before noon, or nominal relative clauses, flights that serve breakfast. These are the post modifiers. These are pre-modifiers and these are post modifiers, and they are all related with nominals. As I said before, Nominals are the main complexities of the noun phrases in English. While we are talking about the nominals with the pre-modifiers, let's look at this problem in English. Okay, we say this flight, we don't say this flights. We say those flights, we don't say those flight. Okay, but in our case, when we do the determiner and nominal, remember that rule? Determiner, nominal, where is determiner, nominal. This one doesn't say anything about these flights or those flight, okay? According to this rule, both this flights and those flights is possible according to this rule. But we know that these two are not correct noun phrases in English. So however, what are we doing wrong? What are we doing wrong with this issue? Okay, we did not make sure that the agreement between two parts of the rule is established. We need to do something about this. So there is this agreement problem. Okay, there is this agreement problem, and usually we don't have this kind of problem in Turkish. We don't do agreement problems in Turkish much. That's why many native Turkish speakers, when they switch to English, they forget to make sure that the agreement is established in a sentence. It happens a lot. But in English, agreement is a problem, and we have to be careful about it. The rule that I gave you doesn't establish the agreement. So what are we gonna do? Okay, what are we gonna do with this problem? Problem is this. There is a single rule that says determiners are nominal, and this rule overgenerates. What do I mean by overgenerate? It will, I mean, if you think these rules are generating sentences for English, it will generate both this flights and those flight, right? Okay, so we have to deal with this problem, and there are many other instances of this problem, and we are going to see them in a few minutes. Okay, let's look at the verb phrases other than the noun phrases. Let's look at the verb phrases. With the verb phrases, the problem again, the verb phrases are as complicated as the noun phrases, but instead of using that nominal invented non-terminal of nominal, we have different types of verbs, right? When we say a verb phrase is a verb, something disappeared. The flight disappeared, I can say that. But there are some verbs that takes a noun phrase, and we call them arguments, like a function argument, right? Verb and noun phrase. I prefer a morning flight. So prefer takes a noun phrase, a morning flight. In this case, this verb takes a noun phrase and propositional phrase. The flights leave Boston in the morning. Okay, so this is noun phrase, this is propositional phrase. And other type of verbs that takes directly a propositional phrase, flights leaving on Thursday. So what I am saying here is we don't see that the solution that is similar to nominal, invention of the nominal terminal. Here we see another type of problem where I have to pick the correct rule depending on my verb. Okay, depending on my verb. You wouldn't say The flight disappear a morning flight. You see? The flight disappear a morning flight. Or I disappear a morning. That doesn't make much sense. Disappear doesn't work that way. Disappear doesn't take a noun phrase. Okay? Leave doesn't take a propositional phrase directly. That's why there is this problem of different types of verbs have different types of taking different types of rules. And how did they deal with this problem? They say that, okay, let's subcategorize these rules. Okay, not all the rules are applicable for all the verbs. Even though there are many valid VP rules in English, not all verbs are allowed to participate. Okay, we subcategorize those verbs, and using those subcategorization, we produce hundreds or more rules, because there are many different types of verbs, and each verb might behave in a different way. For example, for sneeze, you will say John sneezed. For find, okay, please find a flight to New York. So find takes a noun phrase. Give takes a noun phrase and noun phrase again. Give me a cheaper fare. Okay, so each verb belongs to a category, a subcategory. Okay, and there might be hundreds of categories for a given natural language, and finding these categories is a task for the NLP designer. Okay, that will make our job a lot more difficult, because we need hundreds of rules, and each one is applicable for a different set of verbs. That comes from the complication of the verbs. We didn't have these kind of problems, maybe. I mean, well, yeah, we have the same problem with the noun phrases, but it is not as serious as this one. But for the verbs, this is a more serious problem. This is a more serious problem. Okay. As I said before, you cannot say John sneezed the book. You cannot say give with a flight. You cannot say I prefer United as a flight, etc. Right? So the same thing with the agreement phenomena. Remember the agreement: these flights, those flight. Okay, we need a way to formally express the constraints. Okay, our rules are too generic for now. Okay, when you say verb phrase is a verb and noun phrase, then for the sneeze, hapşurmak, right? For the sneeze, I could say somebody sneezed the book, which sounds funny, but our rules are okay with this kind of sentence. Okay, and if I replace this verb with a sneeze, if I replace this noun phrase with the book, both of them are valid, and this kind of overgeneralization is not a good thing. So what are we going to do with the possible context-free grammar solution? I could say this maybe. Remember our agreement problem? Maybe instead of having a single sentence type, maybe I should say singular sentence and plural sentence. Singular sentence should have singular noun phrase and singular verb phrase. Plural sentence should have plural noun phrase and plural verb phrase. And singular noun phrase should have a singular determiner, etc. You understand the point, right? So if I do that, I am multiplying all the rules by 2 for each case. This is singularity. How about the transitive, intransitive? How about the verbs that take a noun phrase and verbs, etc. So for each case, I need to multiply the rules by 2. Okay, I need to multiply the rules by 2. that's going to increase the number of rules a lot. So this is one solution. The other solution is just ignore this, and deal with the overgeneralization later, like we did with the A plus B. Always parse this expression. Doesn't matter A and B are two different types. Later check their types to see if their types match. That's what the compilers do. Maybe that could be another solution. So the whole point here is that context-free grammars cannot deal with the complexities of the natural languages by themselves. Okay, they can take us from one point to another point. Okay, and they might be very, very useful, but they are not powerful enough to handle everything. And if we force them to handle everything, our number of rules increase exponentially, and we don't like it. We have to use some other techniques to deal with the remaining problems. Okay, so the solution that increasing all the rules for each agreement problem, transitive, intransitive problems, word types, it works, but it is ugly. And it doesn't scale that well because interaction among the various constraints. So it explodes, and we have to deal with these kind of problems in some other way. But throughout the literature, they have found ways of modifying the context-free grammars. Okay, and they name them. They give them very nice names: construction grammar, A, L, F, G, and etc. I don't know what they are. I am not going to look at them. But there are some solutions that exist, but I don't want to go into those kind of details. So for now, what we are going to do is we are going to ignore those kind of problems. Okay, we are going to ignore those kind of problems, and we will stay focused with our main problem of parsing a sentence without looking at the agreements or the word types and etc. Okay, for now we looked at the context-free grammars and their relation to the human languages or the natural languages. Let's look at our data at hand. Okay, how we use these ideas in data sets. What kind of data sets we have? We call these kind of data sets tree banks. Okay, they are corpora in which each sentence has been paired with a parse tree or many parse trees sometimes. Okay, if I know the context, out of all the possible parse trees, I pick the correct one. So if I have tens of thousands of sentences, how do I create such a corpora? Given a sentence, I assign a parse tree to it. So let me give you an example. Here is an example. Okay, so this is a parse tree of a sentence. It says that this is a quotation. This is a quotation, somebody saying something. We would have to wait until we have collected on those assets, he said. Okay, this is the sentence, and this is the parse tree of it. So as you see, with the parse tree, there is this noun phrase, but subject is first subject, I guess. Okay, there is verb phrase. Okay, verb phrase again here. Again, a noun phrase, subjective noun. Okay, verb phrase. I don't know the meanings of those. It looks like there are many non-terminals in this rule, but this is a very large data set, corpora. 1 million words from the Wall Street Journal, and each sentence is parsed, and each sentence is assigned a parse tree. Okay, it's called Pen Tree Bank. It's called Pen Tree Bank. So how they did this? They had a small parser, okay. They run this parser, they get this tree, and somebody or two or three people go over this tree. If there are errors, they fix it. This is how usually they do it. They first parse collection with an automatic parser, then human annotators correct each parse as necessary. Okay? And of course, this depends on the part of speech tag set. It is complicated by part of speech tag set. And a grammar, you need a grammar and instructions for how to deal with particular grammatical constructions. So it's a detailed task to deal with this kind of tree bank formation. Once you have this tree bank, okay, that will give you automatically complete tree of the whole language for this 1 million words. Okay, so the tree bank by themselves, they implicitly define a grammar for the language. Okay, so what you do is just you take the local rules that make up the subtrees, and if you put them together, that will give you the grammar for the whole language. Of course, it is not complete grammar of the language because I have only 1 million words in that. Well, it is large, but compared to what I can speak, it is very small. Okay, it is not complete, but if your corpus is large enough, then you may say that I have enough decent coverage of the language. I have the decent coverage of the language. Okay. Well, for simplicity and for the elegance, we like to express our rules using recursive mechanisms, but for the tree banks, usually they don't prefer this because humans are not very good at writing or applying recursive rules. So instead of using recursive rules, they unroll them and they do this. They say that a verb phrase, okay, either this rule or this rule or this rule or that rule. So after the fourth recursive unrolling, they just stop. They say that after that, this is not meaningful. People don't speak that kind of noun phrases or the verb phrases. Okay? In a single verb phrase, I may have at most, okay, flights leaving in the mornings before 10, expensive, etc. You see, you don't use more than 4 propositional phrases. Okay, so these are called linearized. Okay, these are called linearized rules. Okay, so let's go back to the discussion of the heads about, but it looks like I am out of time for this part of the lecture. Let's take 10 minutes of break. After the break, we will continue with our discussion. Okay, let's be here around 15:30. Okay, let's look at this topic of heads again. In a given parse tree, it is important to find the head of the parse tree. We like to know the main central point of that parse tree. Doesn't matter it's a parse tree of a sentence or part of the sentence, such as the verb phrase or the noun phrase. Finding the heads of a parse tree is not an ambiguous thing, actually. It has a nice set of rules, and if you follow the rules, you are going to find the head of the tree. For example, here, workers dumped sacks into a bin. Okay. If you have a noun phrase, that is composed of a determiner and a nominal noun, noun, then the nominal noun's name is the head of this noun phrase. Okay. If you have a propositional phrase, then this part goes there. So the rules are actually, it is there, but in this case here, in this case there, and in this verb phrase, the dumped is important. It is here, and in a sentence, verb is important. Okay. So dump is the head of this tree. Okay. So this is lexically decorated tree, and finding the head is just applying these rules. For a noun phrase, it is the noun part. Okay. For a verb phrase, noun phrase, it is the verb part. That's what to say. Okay. So head finding is not an ambiguous process. It has a very nice set of deterministic steps, and follow these steps, and you're gonna find the head of the whole sentence or the part of the parse tree. Simple set of three traversal rules. Okay, and each one is specific to each non-terminal in the grammar. Okay, the same thing again. With the nominal rules, it is the head from the nominal side. Okay, when we apply this one, it is nominal noun, then the noun part. Okay, when the noun phrase, it is the noun phrase part. If it is a sentence part, then it is a verb phrase part. Okay. So if we have a tree bank in our hand, corpora in our hand, okay, they are important for us to test our parsers. That's one thing. The second thing is for the machine learning applications, when you have a parse tree, okay, tree bank, we are going to use them to train our models. If you have a machine learning model to make a parse tree, and also test them, it is also important. Okay, so tree bank users will come back again when we look at the parse trees in the next chapter, and we are gonna do more stuff on the parse trees later. So up to now, I have talked about the context-free grammars. I said that with a context-free grammar, you will have set of rules, terminals and non-terminals, and given a sentence, you apply these rules and you find a parse tree of a sentence. If you can find a parse tree, then that means that that sentence is within the rules of that language. If you cannot, then that sentence is not in the parse tree. If you find a parse tree, then that parse tree is going to be important for you to do your applications such as machine translation. But parsing doesn't mean that it has to be done with a context-free grammar. Because for some language, such as Turkish, context-free grammars are not that suitable, okay? Because in Turkish, word order is important, but different word orderings changes the meaning of the language. When you say ben okula gittim, gittim ben okula, okula ben gittim, each one is an acceptable Turkish sentence, right? But each one has a different meaning, so each one should parse. I am changing, I have 3 words and I can use those 3 words in any order, and each one is a acceptable sentence in Turkish. So what are we gonna do with this kind of languages? Okay, anything is possible. Ben okula gittim, okula ben gittim, gittim ben okula, right? All of the orderings are possible. So what are we gonna do? I mean, I cannot have anything like sentence, noun phrase, and verb phrase, right? I cannot have things like that. If I do that, I have to have noun phrase, verb phrase, noun phrase, and this is possible too in Turkish, right? So what is the meaning of having a grammar then? I mean, I can parse anything that I like. However, we're gonna find the other stuff. So for these kind of languages, they say that, okay, I don't have to produce a parse tree for a given sentence. Instead, I am going to do something else. I will find the relationships between the words of a given utterance, given sentence. Okay? I am not going to focus on the constituency anymore, because constituency is not applicable for some languages. Instead, we will talk about the relationships between the words. And this kind of approach produces this dependency grammar. Okay? So in a dependency grammar framework, there is a parse tree, but this parse tree is a little bit different. Okay? This parse tree specifies the relationship between the pairs of words. And those pairs of words doesn't have to follow each other. Okay? They will be far apart. They may be far apart in a sentence, but we link them with dependency relationships. Let me give you one example and I will come back to this one. My sentence is this: they hid the letter on the shelf. Okay? Hid is at the top. Okay? I find a relationship between this hid and they using this relationship category or class. Nominal subject. Okay? Hid and they, I related using this nominal subject relationship. Hid and letter is related to each other using this direct object relationship. Letter and the is related to each other using this determiner thing. Okay, letter and shelf is related to each other using this on relationship, and shelf and the again is related to using this determiner relationship. As you see, With this tree, it doesn't matter if head is here or there, or shelf is here or there, right? So it loses all the ordering relationship. It loses all the relationship. So that means what? That means given a sentence, if I produce a parse tree like that, that doesn't mean that I accept this string or reject this string, okay? It is not as powerful as context-free grammars. This is only useful for producing the relationships between the words, okay? So what good is that? It is good to find the relationship. It is good for machine translation. It is good for question answering. It is good for those kind of applications. It is not as powerful as context-free grammars, but still we use it in many places like the context-free grammars, and we call them dependency parsing framework. And dependency parsing framework is better for languages like Turkish. Here are some relationships between utterances between the words in a sentence, okay? One of them is nominal subject, okay? Clausal subject, direct object, indirect object, object of preposition, etc. And like the context-free grammars, with the dependency relations, there are many modified dependencies or argument dependencies, etc. What did I say about the context-free grammars? You might have hundreds of rules, and in this case you might have hundreds of different relationships. And let me give you one example of dependency parse tree. Okay, let me give you it for the Turkish. Do I have it in the images? Okay, good. Ah, come on, this is not accessible. Let me find something accessible here. This is not Turkish. This is not. How about this one? Okay. And this one didn't turn out to be. Okay. Here one example in Turkish, both Turkish and English. Okay. O adam bir elma yedi. So actually the yedi is the head of the sentence. Everything depends on it. Okay. The subject of yedi is adam, or the determiner is here, and object of yedi is elma, and determiner is here. Okay. So if you do the machine translation, when you talk about this adam, you know that this is the determiner, and I can do the same relationship when I do the translation. Of course, the word order changes. I have to do something else for the word order. I cannot keep the same word order, but at least I know how to relate, okay, how to relate the subject with the verb of the sentence, and subject with the determiner of that subject, object of the verb of the sentence, and determiner of the object and the object itself. Okay, So dependency parsing is very useful, and for languages like Turkish, it is much more useful than context-free grammars. Context-free grammars. Languages like Turkish are called fluid languages. Okay. They have free word order structures, and for these kind of languages, dependency parser is much better. Also, dependency parser is much faster than the context-free grammar parses. Okay, it has several advantages. Okay, and it captures the syntactic relationships needed by the applications, such as the machine translation, as I had said before, and this one was just one example. Okay, so how does the dependency parsing work? I think next week I am going to look at this more carefully, the dependency parsing. I am going to show you how the dependency parsing works. Since this is a easier parsing method than the context-free parsing, let me give you some ideas. The first one is optimization-based approach. Okay, so since all we are doing is finding relationships between the words of a sentence, we can make a search in this space. Let's say these are our words, okay, and each one should depend like that, right? So is this a good dependency, we ask, and if it and can I find better dependencies than that? And I am making a search, okay, making a search space. And it might look complicated and time consuming, but if you follow some certain rules, it is better than context-free grammar parsing. The other one is shift reduce approach. Okay, that's a greedy parsing method, and I'm going to show you how we do that. In a context-free in a dependency parsing approach. Okay, so let me show you. Let me go back, and there was a nice paper from. Where is it? Archive paper. Yeah, it's a recent one. Okay, resources for Turkish dependency parsing. Archive paper from, I think, from Boğaziçi University. This one talks about a tree bank, okay, Boğaziçi tree bank, that gives us the dependencies of lots of sentences, and this paper talks about it, okay, and I think we have a number of, okay, there are some dependencies, and there might be some examples in this. No, not that. Okay, here. So this is the sentence. İşte basit bir beyaz gömlek, bir gri kumaş ceket ya da yelek, bir de mavi kravat. This is the sentence. Okay. And the relationships between, as you see, this is one dimension, then this is the second dimension. Okay, and between them we are no, it's not like that. Okay, so these are the relationships. İşte is related to number 5 using these relationships, or number 5 is related to 1, 2, 3, 4 using these relationships. Okay, and so these are the order of these are the numbers for the words. 5 gömlek, 4 beyaz, 3 bir, right? And 1 and 5 is related using ADV modifier, a modifier, determiner, a modifier, and this one is related to the root. Okay, so everything is expressed this way, and we have many sentences like that in this data set. Let me try to see if I can find any other. Yeah, same sentence expressed using a tree form. Okay, what did I say? Number 5 is related to all the others using these relationships. For the humans, this is more readable in a visual way. Okay, and I think the root of the sentence was this one, like gömlek maybe. I don't remember. Do we have anything? Okay, good. Tünele girmeden önce geçtiğim manzarayla burası bambaşka. And dot dot dot. Root is the verb of the sentence. And burası is a case. I don't remember the meaning of these relationships. Okay. So next week I am going to look at how we do the parsing. Okay, how we do the parsing, and I am going to go back and maybe look at one or two of these again. I am trying to find the link for the data set that they have. This is the tool they are using for making these relationships. Okay. Tombul dizleri masanın altından Mahmud'un dizlerine yapışmıştı. Okay. So yapışmıştı is obviously the root of the verb, and punctuation, adjective, nominal, punctuation, and noun. Huh? Okay, these are the nominal, subject, punctuation, modifier, etc. Okay, good. Okay, I think I saw the, okay. If you click on it from the GitHub, okay, you just download the whole thing and you take a look. Maybe next week I am going to look more carefully at this software. Okay, let me go back. And so in summary, what we did today is we looked at the context-free grammars, and we looked at the idea of the constituency. Then we said that with the context-free grammars, constituency, we can come to some point for some languages, But for other languages such as Turkish, constituency, especially the word order, doesn't make much difference in terms of finding the parse trees. So what we do, maybe a dependency parsing is a better solution. So for Turkish, dependency parsing instead of context-free grammars is more useful. Next week, that's why we are going to spend more time on the context-free, both on the context-free grammars and the dependency parsing, but we are going to spend more time on the context dependency parsing, especially for languages like Turkish. Okay, I think I will cut short this week. Next week, I will continue with the next chapter. Are there any questions? I know the midterm is getting late, but next week I am not going to do the midterm. We will talk about the midterm next week, okay?
Professor, may I have a question about the papers, presentation papers?
Yes.
Is it possible to choose a paper which is about the machine translation with neural networks? I mean, is it okay?
Sure, yes, but I didn't talk about the machine translation yet, but as a graduate student, if your interest is in the machine translation, yes, you sure, why not?
Okay, thank you.
Okay, I'll see you next week then.
Thank you.